Well, hello, it's Matt Roscoe here at the University of Montana with a short video about Euclid's proof of the Pythagorean theorem for our course on Euclidean and non-Euclidean geometry. So let's get right to it. I have the handout that I gave you in class here, and we'll just work through the proof using some, I guess, some drawing utensils and trying to make sense of what Euclid's argument is for our favorite, probably one of the most well-known proofs in all of geometry, or well-known theorems in all of geometry, the theorem that a squared plus b squared equals c squared. So the first thing that we notice is that there in italics here is a statement of the proof. He says in a right-angled triangle, the square on the sides subtending the right angle is equal to the squares on the sides containing the right angle. So the squares on the sides containing the right angle, I think what he means is those two that, are adjacent to the right angle have are equal to the square on the side that's built on the hypotenuse. And equal in his sense is equal in area. So of course they're not congruent, but they're equal in area. So we'll have to keep that in mind because he doesn't really use the term area. So let's get to the proof. He says in ABC, let ABC be a right angled triangle having angle BAC right. So I guess the first thing we should notice is that he's calling this angle right here, let me get that closer, he's calling that angle the right angle. So I guess we could, note that. Okay, I say that the square on BC is equal to the squares on BA and AC. So the square on BC is the square built on the hypotenuse, and it's equal to the squares on BA and AC. So those are the two squares on the legs. So in other words, this big area is equal to this area plus this area. So he's going to try to prove that. For let there be described on BC the square DBEC. So DBEC, this thing is a square, so I guess what we can assume is that these are all right angles, and that these lengths are all the same. So I don't know if we want to put little lines through them or not, if that muddied the drawing, but I'll just assume that we know this is a square. And on B and AC, the squares GB and HC. So this is kind of interesting. He calls the square GB and HB. So he's calling it by the diagonal, HC. But I think we can just assume that what he means is that, these guys are also squares. So we have right angles everywhere here. And that these distances are all the same. And these distances are all the same. Okay, well, I guess we have a start. And then he says through A, let AL be drawn parallel to either BD or CE. Okay, so through A, let AL be drawn parallel to either BD or CE. So what he's saying is that this line is parallel to this line and is parallel to this line. And then let AD and FC be joined. Okay, so he's drawing in AD and FC being joined. So he's drawing those lines in, he's adding those to the drawing. Then, since each of the angles BAC and BAG is right, let's see, BAC is right and BAG is right. Okay, since these two are right angles, it follows with a straight line BA and at the point 8 on it. The two straight lines AC and AG not lying on the same side make the adjacent angles equal to two right angles. So it follows that with a straight line BA, and at the point A, on it, the two straight lines AC and AG, AC and AG, not lying on the same side, make the adjacent angles equal to 2 right angles. Therefore, CA is a straight line with AG. So in other words, CA is a straight line as well as these. So he's just proving that when I constructed, I guess, a square on the leg, that since I have right angles here, we have a straight line there. And since I have right angles here, we have straight line there, and so on. So we can rely on this being a line and not sort of a segment, and a segment moving off in a slightly different direction. So that kind of seems interesting. He spends some time in lines 15 through 20 through 24 establishing that sort of these things are straight. So it says BA is also in a straight line with AH. So let's see, BA and AH, there it is. And since the angle DBC is equal to the angle FBA for each is right, let the angle ABC be added to each. Let's see, DBC, let's be careful here. DBC and FBA, each is right. DBC is this one, DBC. So we're sort of, I guess, DBC, that one. And FBA, he says they're each right. So this one and this one are each right. So I'll just sort of highlight that with, okay, they're each right. He says, let the angle ABC be added to each. So I guess the angle ABC added to each is sort of this angle in here. Okay, so ABC added to DBC makes DBA, right? And ABC added to FBA makes FBC. So then he says, therefore, the whole angle DBA is equal to the whole angle FBC. I think that's what he was winding up for. Let's just mark those in. DBA, let me see the best way to draw that. This whole angle here is equal to this whole angle here. And the reason for that is because each of them is a right angle plus a shared angle. And since DB is equal to BC and FB to BA, let's try that. Let's see. DB is equal to BC. DB is equal to BC. Certainly agree with that. And let's get a different color here. FB is equal to, yeah, he says FB is equal to BA. Okay. The two sides AB and BD are equal to the two sides FB and BC. AB and BD are equal to the two sides FB and BC. So I guess he's naming them in order. A to B, B to D, F to B, and B to C. So those two sides are equal in that order. And the angle ABD is equal to the angle FBC. So that's just what we have from above in pink. And the two sides, let's see, let's get the color coding right. AB was a blue side and BD was a green side. And FB was a blue side and BC was a green side. He says, therefore, the base AD is equal to the base FC. The base AD is equal to the base FC. So how does he get that? Oh, I see how he's getting that. So he has side, angle, side. So what would we do there? We could draw in this triangle here. And we could draw this one in with, say, polka dots. So he's saying that this length here, right, is equal to this length here. And I think he's going to say, and the triangle ABD is equal to the triangle FBC. So I would argue that these two are sort of switched up. He first shows side, angle, side up here. And from it, he gets that AD and FC are equal. So AD and FC are equal. How's that feel? So basically, this triangle overlaying that triangle have to be equal because side, angle, side, is equal to side, angle, side. And he says triangle ABD is equal to triangle FBC. So by here, what he means by equal, he means equal in area. They're also congruent, right? So I guess either way, equal in area or congruent. And here's where the argument's pretty interesting here. Now the parallelogram BL is double the triangle ABD. So the parallelogram BL. So B to L is this parallelogram right here. Those really, it's a rectangle, right? Maybe what I could do is somehow highlight it using yellows. And what he's saying is that this parallelogram BL is double the triangle ABD, and ABD is the one with the lines through it. And I guess the way to see that is, the one with the lines through it here has, a base of this and a height equal to that, right? So if the triangle ABD has the same base and the same height as the parallelogram BL, as he calls it, then we could kind of think of it as half its area, right? Well, we can definitely think of it as half its area because it's 1/2 base times height, where the base and the height are the same. Sometimes it's easier to see this if we turn, this sideways and take a look at this. This would be the base of this triangle, the triangle with the lines through it, and that would be its height, the vertical distance above its base, perpendicular to its base. And that base and that height is the same as the area of this yellow region. But since this is half, two of these fit in here. I hope that makes sense. And he says the square on GB is double the triangle, so I'll call the square on GB is double the triangle on F. And I should say ABD. So I guess this one was the lines triangle. So I'll this is the lines triangle, and this is the polka dots triangle. But he says the square on GB is double the triangle FBC, and FBC again is the polka dots triangle. square here, he's saying so maybe I can make a few notes here. I would just say yellow is double line. I'll just say triangle ABD. So this yellow here, and this yellow here, he's saying triangle FBC. And again, the reason is similar here. If I look at FBC, this triangle right here, the one with the polka dots in it, we can see its base is this and its height is that, because it's just been drawn over here, right? If I extended this out and took a look at its height, it would be that distance, which is the same as this distance here, the perpendicular distance above the line containing the base. And so, you know, if I slid this over to A, it would have the same area, that the polka dotted region would have the same area, and we could see it as half of the area of the yellow, I guess, square. And I think it's kind of fairly easy to see where he's going to, but it says, but the doubles of equal are equal to one another, right? So really what he's saying is yellow equals yellow here, right? If this is double that, and that is, you know, this triangle, and that triangle is congruent to this triangle, and this yellow area is double that lined triangle, then these two yellow areas have to be the same. So it seems really unlikely, because this is sort of tall and skinny and this is a square. We have a rectangle here that by this argument, these two figures have to be exactly the same in area, because each one of them is double the area of two congruent triangles. I hope that makes sense, because we're almost to the end here. It says, therefore the parallelogram BL is also equal to the square GB. I mean, so I guess, you know, what we have here is, you know, yellow is equal to yellow. And he says, similarly, if AE and BK are joined, so now he's saying AE and BK, the parallelogram CL can also be proved equal to the square HC. So the parallelogram CL, let's see if I have a different color. Let's use orange. Parallelogram CL is this one. Can also be proved to be equal to the square HC. The square HC is this one. And he's not going to prove it, but I think that the way he would do it is he would use, again, this triangle here and this triangle here, and show by side, angle, side, that it's equal to, let's see, if it was side, angle, side, then this one would have to be, so side, angle, side would be that one. We'd have to go for this one, side, angle, side. So you can see there are a triangle and a triangle here, and each of those triangles is half of these two areas, and since those triangles are congruent, then double their areas would have to be equal. And so he says in the very end, therefore the whole square DBC is equal to the two squares GH and HC. So the whole square BDEC has to be the sum of these two, and you can just see it in the area. The yellow is equal to this yellow, and the orange is equal to this orange. And so literally, you know, this area plus this area have to equal to these two areas. And what we've really shown is that the square drawn on the hypotenuse is equal to the sum of the two squares drawn on the legs. And I think that's all you'll have to say here. He says, and the square DBC is described on BC. In other words, it's constructed on the hypotenuse. And the squares GB and HC on sides BA and AC. So therefore, the square on the side BC is equal to the squares on the side BA and AC. So the square on this side is equal to the squares on this side. And A squared plus B squared equals C squared. I hope that makes sense. So this is really just a sort of summary of what has been shown. So standing back from it a little bit, it really relies heavily on triangle congruence. It also relies a little bit on sort of this idea of a shear, that you can take a triangle with the same base and the same altitude and pull it out, right? So, in a sense, this triangle right here is the sheared half of the triangle formed by the diagonal here. And the dotted triangle here is the sheared half, right, of the triangle in this particular square here. It's been pulled out. And this one has been pulled up. A has been pulled up. So there's some really interesting ideas. And one of the things in your book, mentions is that rotation is involved here. He doesn't really ever rotate anything, but you can see that if you rotated the lined triangle about the point B 90 degrees, you would get the dotted triangle, right? So there, you could think of it as rotation, but that's basically it. I hope that makes it clear. If it doesn't, we'll be back together on Monday. I'll go ahead and scan these two drawings and add them to our list in Moodle, and in case you want to review, I guess, my thoughts and my notes here. I hope that the coloring made it a little bit more obvious what's going on. We'll get together on Monday and talk it over if you have confusion. But remember that your goal is to create a GeoGebra file that sort of makes clear, how this proof proceeds. So you want to think about how you could use checkboxes and colors and verbal descriptions to help students walk through the arguments that are present here. I look forward to seeing what you come up with. It's a fairly complex argument, and it certainly could be aided in understanding by a dynamic sketch of how the argument proceeds. Okay, we'll stop there and wish you a happy weekend and see you all on Monday.